Okay, now let's do a problem of multivariable calculus type where we're using differentials to estimate error again. The example says, suppose that the width W of a rectangle is measured to within a relative error of 0.5% of its actual value, while the length L is measured to be within 1.75% of its actual value. If these values of W and L are used to calculate the area, use differentials to estimate the relative error in the calculated value of the area. Alright, so I'm just going to write something on my little board and then we'll get over there. The width, let's see here, so I'm going to write down relative error in W is less than 0.005. I'm going to get the error in the length is less than 1, okay, that's 1.75%. Hold on, like this. Okay, let's do that. Yay, okay. So they give us two relative errors. They tell us the relative error in measuring the width is less than 0.5%. They say the error in measuring the length should be less than 1.75%. And what they want, right, is just how that affects our calculated area. Now, following the same sort of example that we did in Calc 1, what we want is a formula involving area, length, and width. Well, that's a nice easy one for a rectangle. So I'm just going to write that down. Yay! Now if this is Calc 1, we start taking derivatives. But this is multivariable calculus. We take differentials. Now remember our formula for a function of L and W. We'll write down the formula first. We won't do this every time, but we'll do it this one time, right? We know that dA should be something like FL dL, yes, plus FW dW, like that. So I'll start putting in what we're supposed to be writing. What is FL? Well, it's the partial derivative of our formula with respect to L. Well, that's just W, so I write down W, and then I write down DL. We'll interpret that in a minute. Then I'm supposed to write down FW. What is FW? It's just the partial derivative of our area formula with respect to W. That's just L. And then I'll write DW, like I'm supposed to. We'll interpret that in a minute, actually right now. How are we supposed to do this? If you're going to be a math major, you're going to be doing differential geometry, and this is going to be a linear transformation. But if you're going to be any other kind of scientist, when you see all this D stuff, you think delta. So this is, should just think delta A is approximately equal to W delta L plus L delta W. Now what do we want? We want the absolute value of A over A. So this is what I'm going to do first. People aren't going to be happy with me. I can't just pick absolute values over the whole thing. What we can do, and it's enough that works, this is called the triangle inequality. It says if you take the absolute value of a sum, that's going to be smaller than what you get when you take the absolute value of each. Because if you take the absolute value of each, there's no canceling that could happen. On the other hand, if you're in your linear algebra class, you may have actually proved this. Okay, what do we want? We want the size of the absolute error, so that's the actual error between the measured area and the actual area, and we divide everything by A. So I divide that by A, yes, and I divide this by A. Sneaky, sneaky, yes, that is equal to A. Divide by this, like that. And so what we're going to get is this final thing where we're going to say delta A over A is less than, what am I going to do? The W's cancel. They're both positive, so I'm not going to worry about that. So this is going to be delta L over L. The L's cancel. They're both positive. I don't have to worry about that. So this is going to be length W, the error in W divided by W. And we have numbers for both of those, right? The relative error in measuring L was less than 0.0175. The relative error in measuring W was 0.005. 005. I think this is going to be 0.005. 0.0225, like that. So something like 0.225%. So pretty small, but that's how it goes. We try to write down the errors they give us using deltas. We try to write down the error they ask for using deltas. We find a formula involving just the variables, and then we take the differential of both sides. Right? Remember, this actually, we got this from tangent planes, so that there's a lot of geometric underpinning here. Once we write down the actual differential, we interpret that in terms of areas. We use a triangle inequality so we can break this up into something that's less than stuff we know. We put in what we know and we're done. That's it.